All right, welcome back, everybody. That was a second test, and as many of you know, we had, oh no, where did it go? All right, I have to move back. There we go. All right, perfect. As you know, it was curve, and so I wanted to tell you something about that because we had a natural 100. Somebody actually made 100 on that exam. See, I told you it was possible. And so because of that, I couldn't do just a give everybody 10 points thing. So I did what was called a Gaussian curve. So the closer you were to 100, the less points you got, but the further away you were, the more points you got. And the class average ended up being 75. But it wasn't naturally a 75, so I'm wearing pants today instead of a kilt. So that being said, let's go ahead and start our last 4 chapters. Here's where things start getting fun or difficult. But they're not difficult if you follow some of my special advice here, okay? So we're starting on all reactions on the alkenes and alkynes right now. So we learned how to make them, and we learned that we can make them 2 different ways. And so we have those 2 reactions we got to play with. Those are E2 reactions, right? And then an E1 reaction for the dehydration of alcohols. So we need to play with that. And so what I'd like you to do is to go to the campus site and look up a reaction table. Okay, it's going to be blank. It's going to look like this. And I want you to start. Oh, sorry. Laptop. There we go. All right, I want you to start filling this out for the last chapter. And you can also do substitution, although that's just one type of reaction. But here we're going to see, this is like with this one right here, we're going to do an addition reaction. We're going to add water across a double bond. So this is our general starting material. The R means it can be anything. I want you to get used to looking for the change. What's changed? Because that's where you have to do the reaction. The rest of it, you tack it on later, but look for the change. So our change here is going from double bond to 2 single bonds. We need water and acid to do it. Is there stereochemistry associated with that? And the answer is yes, and we'll learn about that today. And then basic mechanism is, does it form a carbocation? Is it SN1, SN2, E1, E2? If it forms a cation, then you gotta say, okay, that's rearrangement. And this is actually in chapter 8. But anyway, so if you go back and start filling this out, and then you can start looking at it going, oh, that's really the way I need to remember these things. And then what you can also do is in the book, at the end of the book, it gives you a summary of the methods for preparing things. So here we have the 2 methods here where we dehydrohalogenate. In this case, we do the dehydration of alcohols. This is in the end of chapter 7. So you can use that. If that reaction appears at the end of the chapter, it should be on your reaction table, okay? And then you can use that reaction table to study for you. Now, in the end of even after the problems there's one of these. And I like this because this is starting to make you think about multi-step synthesis, which is what I'm going to talk to you today about, and how we can do it. So in this case right here, we can go with something with a leading group using usually an alkyl halide, have it lead, go to an alkene, and then we can actually add HCl across that double bond twice or once to give us, or if we're adding chlorine across, a halogen across it. This is the reaction we're going to learn today. But then you can take that, since you have a vicinal dihalide, and you can actually turn it into an alkyne. And that alkyne you can turn into a cis alkene using Lindlar's catalyst, or a trans alkene using our dissolving metal reduction, or if you just want an alkane, you can go to here. So see how you can get from a ketone all the way up to an alkyne. So this kind of understanding how chemistry works, start looking at this and pondering it and saying, oh, how do I get from here to here? Well, we have to add 2 halogens across this and then turn it to make it into this, and then turn it back into that. So we're going to see that forwards and backwards. Okay, which brings us to the last slide of chapter 7. Okay, I didn't go over that because I wanted to do the review and I wanted to introduce this today because with reaction tables. So let's say we want to devise a synthesis for putting one cyclohexyl, one butyne from an alkyne and an alkyl halide. Okay. So we know that we can use the acetylide ion as a nucleophile. Okay. So the idea here is that I think we would want to cut the molecule here and here because it says we can use an alkyne. Okay, and the simplest alkyne to use is acetylene. And so if we were to use acetylene, we could deprotonate that, turning it into the acetylide ion first. So we'd have to do that, and then we'd have to have something to do it to make it have this ethyl group on it. And then we'd have to have something else to allow us to put our cyclohexyl on. So that means we're going to have a cyclohexyl that's a halogen. We're going to have an ethyl group that's a halogen. And we're going to have to do a stepwise reaction because then we have to put the other one on here to get to, to get to our reaction here. So knowing that we have to start with these two materials and this material, and knowing that we can turn this into a nucleophile and do a substitution reaction on each of these, we can start by saying, okay, acetylene right here, and we're going to do sodium amide N2 right here in our first step, and on our second step, we're going to do ethyl bromide. And what that's going to give us is our first one right here with a hydrogen here. And then our second one is going to be, again, sodium amide. And our second step is going to be the cyclohexyl with the benzyl group on, bromine on there. And that's going to give us our final product. So the key steps here is to, number one, figure out what you're allowed to use, which is an alkyne and an alkyl halide. Number two, what reactions do you have to do this? We know that we can make acetylide a nucleophile, which means we know we can make those two bonds. So then we go, how do we make those two bonds? We know we can do it with substitution reactions. And then you just put them in order. Now, could you switch the order of this, the addition of this or this right here? Put the cyclohexyl on first? Yeah, that would be appropriate as well. Okay, so this is retrosynthesis, okay? So when we do our reactions that we're going to learn today, what I want you to be able to do is look at it in this way here, okay? I want you to think of it as, okay, I know how to do this reaction here, okay? So I'm going to make some kind of memory thing so that I can say this plus this equals my last part. But then you also need to think of it as, oh, if I have this and I have this, what do I need? What reagent do I need? So put a blank there and try to figure out what this is. Okay, so be able to go forward, but also fill in what the reagent is. And then the last way to do it is to say, okay, I have this reagent and this is the product. What did I start with? So being able to look at the reaction in three ways, look in the reaction in three ways: the forward with the starting material and the reagent, the forward with the reagent, the starting material and the product, filling in the reagent, and then starting with the reagent and the product and figuring out what the reaction started with. If you can do each reaction that way, you are going to do very well in this class. Let me just tell you that. Okay, questions on that? Okay, so let's go into taking roll. Oh, I can take my mask off while lecturing. There was a slight bump 2 weeks after spring break. It came up to 4.75% testing positive, and it dropped today to 3.75. So that might have been our spring break bump. I'll keep monitoring. All right, everybody got that? Okay. All right. So today we're going to talk about addition reactions. So we did elimination reactions. We know there's 4 kinds of general things we're going to do: substitution reactions, addition reactions, elimination reactions, and rearrangements, right? So this is our addition reactions. And so we're going to start with alkenes and alkynes and add stuff across that double bond. Okay. So the idea here is we're going to take our pi bond here and turn it into 2 sigma bonds on our product. So one's going to be on one of the carbons and one's going to be on the other one of the carbons. Okay. So that is where we're going to look at this. And so when we look at this, we have to think of the alkene is the nucleophile. It has the electrons in the double bond that are going to be used to make one of those sigma bonds. Okay. So it has the electrons to make them sigma bond. And therefore they're going to react with electrophiles. And we're going to talk a little bit more about that. Okay. So there are 2 ways that we can add something across a double bond. Okay. We already talked about one of them in the last chapter. It was syn addition, where both things add on the same side at usually the same time. So they add at the same side right here, and you get this syn addition. And so they're on the same side. So that controls your stereochemistry and your regiochemistry, right? Because whatever your groups were in the alkene, they are still in those positions when they form the new tetrahedral carbon structure. The other thing that we can do here is we can actually add 1 to one side and then 1 to the other side. Okay, and we call that anti-addition. Now notice that's going to give a different product because of where your 2 groups were here. So it's regio-selective. We have to play with it and make sure you understand which side is adding where. And we have a few rules for that, and we're going to go through all of those rules. Okay, questions? All right, so we're going to come back to this, but these are all the reactions. So I'm done lecturing, just write it down. No, I'm kidding. Okay, so what I'm showing you here is that we have all these different reactions and they have different regiochemistry you have to worry about. So in the first one here, we can add HCl across a double bond. Well, because we took HCl away from a double bond, all we have to do, we can add it back. And this will do syn and anti-addition. Okay, and I'll go through each of those and why. In the last reaction of the last chapter, we saw we could dehydrate alcohols. Well, you can dehydrate alcohols if you have a lot of acid and a little bit and no water, and it turns it into the alkene. Well, if you add a lot of water and a little bit of acid, it turns it back into the alcohol. And it also has syn and anti-addition. We can add halogens across there. So you have 1 halogen on each. That's how you get those vicinal dihalides. And then you can also do a special reaction where you add a halogen first and then an oxygen second. And then we call that the Halohydrin reaction. Then there's this weird reaction right here. In this weird reaction here, boron is actually is electron deficient, and therefore it doesn't act like other reagents and it will add backwards. So it adds syn, okay? And then we have another reactant here, which has mercury in it. In this mercury one, which we call oxymercurization, demercurization, because the mercury comes off, we can get mostly anti-addition, but some syn. And then, of course, we're going to have 2 other reactions where we're going to decompose alkenes. We're going to make a diol, or we can actually just reduce it down to that. We've already seen this in chapter 7. So those are all the different reactions we're going to look at in this chapter, but we're going to pay specific attention to the regiochemistry and where the additions of the materials go. Okay, so in the first one we have hydrohalogenation. Basically, you're going to add acid across the double bond. Okay, so the first thing that's going to happen is your nucleophile, which is the nucleophile, the pi bond, the alkene. The nucleophile is going to attack the electropositive side of the acid. Okay, so that means the hydrogen, because this is a polar bond, right? We have the bromine as a polar bond, more electronegative than hydrogen, and therefore This is the partially positive side. And so the alkene is going to take its 2 electrons, reach out and grab that hydrogen. When it does that, we're going to form a carbocation. Okay. And when we form that carbocation, we now have the bromine acting as the nucleophile. It's going to come to the electron deficient carbon and make that new pi bond. Okay. So in this case here, we're following proper rules of where nucleophiles attack electrophiles, right? That makes sense because the alkene's reaching out and grabbing the hydrogen. The bromine keeps its electrons. Now it's negatively charged and it's going to come in and react with the carbocation. Okay. So the idea is that when that happens, that's a really fast step because we already have a positive charge. The slow step is waiting for the alkene to reach out and grab that hydrogen away from the acid. Okay. So it's basically just 2 Lewis acid-base reactions, right? Because this is our Lewis base and this is our Lewis acid, but our substrate now becomes our Lewis acid and our bromine is our Lewis base. And when those react to form our new sigma bond, okay? So notice that we have a carbocation, right? What's the shape of a carbocation? It's trigonal planar with an empty orbital above and below. That means the anion can touch the top or the bottom. So it can give you syn addition or anti-addition, depending on which side of the molecule it attaches. That's why its regiochemistry is syn and anti. Okay. So in this case here, because we have 2 different acid-base reactions happening, our diagram looks like this. Okay. We have our first activation energy getting us for our alkene to reach out and grab that hydrogen. So in that transition state, we're moving electrons from here to here and electrons from here to here. Okay. So those are the bonds that are making and breaking all at the same time. Then we form that intermediate, that higher energy intermediate. The carbocation is higher in energy than the starting material, but it has a lower activation energy, so it's fast, and then it makes our product. And most of these go from an alkene to something with only sigma bonds, and those tend to be more stable, therefore that these reactions tend to be exothermic. Okay, so let's figure out where we're going to put that positive charge, that carbocation, because that's going to control our regiochemistry as well. Okay, so we have a rule for this to make it easy. We call it Markovnikovs Rule. Markovnikovs Rule says that the carbon with the more hydrogens will get the hydrogen. Okay, write that down.
What?
The carbon with the more hydrogens is going to get the hydrogen when the alkene reach out and grabs the hydrogen off the acid. Okay? But why? Well, that means the other carbon has fewer hydrogens, right? And the other carbon would have carbon-carbon bonds. What's the most stable carbocation? Secondary carbocations and tertiary carbocations, right? So if you're going to form the most stable carbocation when you do this, that's why you always add the hydrogen first to the one with the most hydrogens. Okay. So yeah. All right. So it all has to do with that carbocation stability and the activation energy to make the less stable carbocation. Okay. So in the case here, we have an alkene. Okay. Now on this side, this carbon right here has 1 hydrogen on it. This carbon over here has 2 hydrogens on it. Okay. So which one's going to get the hydrogen? The one with 2 hydrogens on it, right? Okay. And so if we look at that, that would give us this product here because it's going to add a hydrogen here. So now we have 3 hydrogens on each side and we have a secondary carbocation. Okay. And then of course it reacts fast like this. So that secondary carbocation is more stable than the primary carbocation. Okay. So that means that the activation energy to form the secondary carbocation is lower than that to form the primary carbocation here. In the primary carbocation, it's very hard to make primary carbocations, so it's not going to happen. And even if it did, it was going to be such higher energy. And then eventually they'll come down to actually giving us the least thermodynamic product anyway, because the bromine is on the outside. So always look for making your most stable carbocation. That's Markovnikovs Rule. Okay. So let's talk about the stereochemistry of it a little bit. We're going through a carbocation. So that means we're going to get a 50-50 mixture of our product. It's going to be a racemic mixture if it was had a chiral center. Okay. And it has to do with the idea that our carbocation has this big empty orbital. And whatever the halogen in, it's going to give 50% top, 50% bottom, which is going to give us a 50-50 mixture of that. If we have two hydrogens on one of those, on that carbon, on that stereo center, then we obviously don't have stereochemistry. But in this case here, we have four different things on each of our materials. So we have regiochemistry. The halogen is going to go on the more substituted carbon. The hydrogen is going to go on the less substituted carbon. And stereochemistry. It's going to give us a racemic mixture. Okay, does that make sense? Okay, all right. So let's move on to a different reaction. It's going to be similar, but what we're going to do here is we're going to add water across the double bond, and we're going to do it with a catalyst, okay, the catalytic amount of acid. When we dehydrated, we used a whole bunch of acid and no water so that we could pull the water into the acid and give us our alkene. We're going to do the reverse reaction. So we're going to add water, but we still need the acid to help us along. Remember, we needed acid to get us to the alkene too. So what we're going to do is we're going to take our double bond here, and we're going to add H to one side and O to the other side. Okay. So what does that mean? Number one, Markovnikovs rule applies. We're going to put the hydrogen on the side with more hydrogens. We're going to put the oxygen on the side with more carbons. Okay. We can have rearrangement because it goes through the same mechanism of a carbocation. And if you replace water with an alcohol, the reaction still works. The hydrogen still goes to the side with more hydrogens, but the oxygen that's already bonded to carbon is going to go to where the carbocation is, giving us an ether. So it's basically the same reaction, but we replace water with alcohol and it turns it into an ether. Okay, so that's the carbon, oxygen, carbon structure you should remember, but I'm going to tell you. Okay, so what is the mechanism? Well, it's the same as the other one. But here we're going to start with the hydronium ion right here. So that's a very acidic proton. So that means that our alkene is going to reach out and grab this and leave that electrons on the oxygen. So that gives us our hydrogen on the most hydrogen side and our carbocation, preferably a secondary or a tertiary. Okay. Now, the fast step is when our water now acts as our Lewis base. Our carbocation is our Lewis acid because it's electron deficient. And it reacts to form this oxonium cation. Okay, so we formed our new sigma bond. But we still have a charge because it was a neutral oxygen coming in. So all we have to do is have a molecule of oxygen come in, reach out and grab that extra hydrogen off the oxygen, taking our formal charge down to 0 for oxygen, giving us our neutral species and giving us our alcohol and regenerating our acid so it can be used back at the top. Okay. So this is acid catalyzed, okay? So because we formed a carbocation, that means we're going to have the same stereochemistry that we had before. We're going to have the same stereochemistry as the hydrohalogenation. We're going to have the same regiochemistry. Hydrogen's going to go on the more hydrogenated side. And we end up getting our product. So does that mechanism make sense? So basically the energy diagram is going to look exactly the same as the halogenation, but we're just adding water across that diagram. All right, any questions? Okay, good. All right, so now there's another way to do it, but what if you don't want it to rearrange? What if you had something that it could rearrange to give you a tertiary carbocation with your alcohol in the wrong place? Okay, well, you have to use a different reagent. In oxymercurization, demercurization, it doesn't form a carbocation, so it doesn't rearrange. So it stays in put. When you do those first two reactions, you have to look for carbocation rearrangements. In this reaction, it eliminates it. So what we do here is we have a two-step method. We're going to take mercury acetate with water, and that's going to add across our double bond Markovnikovs style, giving us our hydrogen on our more hydrogenated side and our oxygen on there. And then before the reaction's done, we have to break off this mercury by doing a reduction. And this reduction is with sodium borohydride. Okay, sodium borohydride. We're going to talk about sodium borohydride and another reducing agent in a little bit later, but we're introducing it here. Okay. Now you get a mixture of syn and anti, even though you don't form a carbocation. Okay. So that's kind of cool. I mean, it doesn't need acid. It's get good yields very fast. Unfortunately, it uses mercury. Okay, mercury acetate. And so that's the downside of this, but you can make very high levels of unrearranged alcohols in this system. So, and just like with the hydrohalogenation, if you replace water with an alcohol, you will also make an ether, and it will also follow Markovnikovs Rule, not rearrange. Okay, so and yeah, so and note this here. Don't worry about the mechanism for this reaction. Just note that it's Markovnikovs and it's a mixture of syn and anti. It is in the book, by the way, if you just don't even know. Okay, so we have a way of making an alcohol by adding water and acid, but it can rearrange because it goes through a carbocation. We have a way of making an alcohol that doesn't rearrange. So we can make a secondary alcohol with that one, easier, right? So now we have a third reaction. And the third reaction actually goes anti-Markovnikovs, meaning it's going to put the boron on the side with the most hydrogens. And when we oxidize the boron off, that's where the alcohol is going to be. So we can make primary alcohols with this reaction, okay? So interesting, you can make primary and secondary alcohols with the hydrohalogenation. You can make secondary and tertiary alcohols with oxymercurization, demercurization. Here you can make primary alcohols. You can't make primary alcohols with those two others because you can't form that primary carbocation. Okay, so we have a bunch of different reagents we can use here, and the three most common are borane, which is BH3. So if you see BH3, think hydroboration. And then there's going to be an oxidation step with peroxide. Or there's diborane, B2H6, or occasionally we'll use 9-BBM. I think for all of your homework, all three of these are stated in the homework and or quizzes. So those are the ones you need to remember, okay? So in this case here, we're going to add across the double bond in a slightly different way. Okay, let's see. I don't have the mechanism here. Okay, so what happens in the mechanism is that we actually have a hydrogen, boron, and the boron is trigonal planar right here. And so what it's going to do is it's going to add the boron to one and the hydrogen to the other at the same time. Forms this four-membered transition state. And that's why the boron transfers directly to the least hindered carbon, and the hydrogen goes to the more substituted side. Think of it as this is the big group here, so it's going to add across the less sterically hindered side. Okay, so it's a less sterically hindered side. That's why it goes anti-Markovnikovs, because it's too big and we're not forming a carbocation. So this results in syn addition. So it adds across the same side, just like catalytic hydrogenation. We're adding the boron and the hydrogen at the same time. And when we do that, we have syn addition and no carbocations. And again, we're going to do primary alcohols. Okay, so these are our three choices so far. We can add acid and water, acid catalyst and water, and get an addition across that is Markovnikovs because our hydrogen goes to our more substituted side, and we get alcohol. But we can get rearrangement. Okay. Now, with oxymercurization and demercurization, we're going to follow Markovnikovs rule. We're going to get our hydrogen on our more substituted, on our more hydrogenated side, and our alcohol on our more substituted side, but it will not rearrange. So you will be able to make a secondary alcohol in the presence of other groups. And in hydroboration oxidation, which is the second step is with this peroxide, hydrogen peroxide, we're going to see that borane in the first step. The boron's going to add to the least substituted side. The hydrogen's going to add to the more substituted side. And when we oxidize off the boron, we get it on there. So how do we want to look at this when we're doing our homework on our quizzes? Okay. Well, if we have this alkene right here, by choosing your reagent, you can make a primary, a secondary, or a tertiary alcohol. Interesting. Okay, so why would this give us a tertiary alcohol? Well, remember that first step is adding that hydrogen here. We got our carbocation here. That's a secondary carbocation. We have a hydrogen here. It can do a 1,2 hydride shift, shifting the carbocation here, shifting the hydrogen over here. And that gives us our tertiary carbocation, which gives us our tertiary alcohol. Okay, so it didn't start out as a tertiary carbocation, but when you have a carbocation that can rearrange to tertiary, it will. And it's a very fast rearrangement. And then, of course, you get your alcohol on here. Now, in the oxymercurization, demercurization, your mercury is going to add to this side, Hg, and then your hydrogen is going to add to this side. And then you're going to reduce off your mercury, giving you OH here. And that you have your secondary alcohol. Excuse me. It can't rearrange, so it gives us our secondary alcohol. And with the hydroboration demoration, we end up going to getting the boron on this side, getting the hydrogen on this side. And when we oxidize off the boron, we get a primary alcohol. Okay. One substrate, 3 different alcohols by choosing your reagent. So selectivity in reagent is what we need to focus on for the rest of organic chemistry. Okay.
What?
For the rest of organic chemistry. Reagent selectivity. So water and alcohol will give you secondary and tertiary. I mean, water and sulfuric acid will give you secondary and tertiary alcohols. The oxymercurization, demercurization, they do not rearrange. Whatever you started with, it's going to give you that. And they both follow Markovnikovs rule. The hydroboration oxidation is the opposite of Markovnikovs rule and gives us primary and secondary alcohols, depending on the substrate. Questions? All right. So one type of alkene gives us that many different alcohols. Okay, so I'm going to switch gears a little bit. So now we've added hydrogens across something. We're going to do, I mean, we put one hydrogen in some other nucleophile, okay? So we put water or mercury or boron, right, on this. And so now we want to do something a little different, and it's a different mechanism, okay? We're going to add a halogen across the double bond, okay? So in this case here, we're going to break our double bond. We're going to add it across this. Notice the conditions here, okay? The conditions are dark, room temperature, and a solvent called carbon tetrachloride, okay? Carbon tetrachloride does not participate in the reaction, but it's a solvent that cannot be halogenated, okay? So that's why we use it. Carbon tetrachloride is just the solvent. It does not participate, okay? But we have to have it dark and room temperature to keep it from reacting in a free radical form. We're going to talk about free radicals in chapter 10. But what we're saying here is it's not a free radical mechanism, and so we want to keep light out because that could induce it. So it could be chlorine or bromine. Turns out iodine is not reactive enough. It's an endothermic reaction, and fluorine is too reactive. It practically explodes. So the only useful two are the chlorine and the bromine. Okay. So and so we don't really have one that's definitely the nucleophile side and one that's definitely the electrophile side, because we have a non-polar bond. So we have to have a slightly different mechanism. Okay. So what we're going to do is we're going to have that induce a dipole on our double bond, having it come in and say, oh, I'm going to try to add some electron density to this side, and that's going to make one side partially positive and one side partially negative. And when we do that, then you react. Okay. But the cool thing is that because this mechanism is a little bit different, you do not rearrange. And you only get anti-addition. Okay, so what anti-addition means is one on one side and one on the other. Okay, so let's talk about that. Okay, because we have induced this dipole with the system here, two of the electrons from the bromine or the chlorine come down here. These two electrons come up here, and we make this polonium ion. Okay, so that's sitting on top of your alkene. So your halogen came up here, and it's positively charged. Your other part came off as the anion. Notice that we break the bond here. We're breaking the bond here, giving both of these electrons to the leaving group, which in this case is the halide, the chloride or bromide ions. Okay, so now this is why it's anti-addition. This cannot attack the top of where the alkene was. It can only attack from the bottom to bind to one or the other of these carbons. Okay, so what's the next step? Well, we have to have our now nucleophile. Our halogen is now the nucleophile. And this is actually a substitution reaction because this acts as our leaving group. One of its sigma bonds breaks, but not the other. So it stays sigma bonded to the other carbon, and we made a new sigma bond with the halogen. So we have them shown in their anti-configuration because one adds to the top, one adds to the bottom every time. Okay. Okay, so let's talk about the stereochemistry of that halonium ion here. We're going to use chlorine in this one. We're going to use an alkene that is in a ring. So we'll definitely know which is the top and which is the bottom. Okay. So in this case here, if the halogen comes in from the top, it's going to form the halonium ion on the top of the cyclic alkene. Now it's an alkane. And then our chloride ion has to attack from the bottom. And these are both equal carbons. It could do either one. But when it does that, it gives us this. And it gives us the trans product always, because it's an anti-addition. So one's going to be on the top, one's going to be on the bottom. But what if, the chloride came and attacked from the bottom? Well, that's going to give us a different intermediate. Well, no, it's not, because if you flip that over, it's achiral. It's the same. You just have to flip it over. It's the same. And you have the attack of the chloride ion, and it can be on this side or that side, but we're going to take that side. And when it does that, we still get our trans product, but we now have enantiomers of each other. So even though we're getting anti-addition, we can have stereochemistry. We can have it attack at either side, giving us our enantiomers or a mixture of racemic. So that means our stereochemistry, when we have this, it's going to give us a racemic mixture because you don't know which side is going to form the halonium cation, and then the halogen will come in from the bottom. So let's dig into the stereochemistry a little bit deeper. If we take the 6-butene and we react it with bromine, we're going to make that halonium ion. Let's just put it on the top first. And then we're going to have attack at the bottom by the other one. So that we're going to end up with, in this case, this enantiomer. See, the bromine came on the bottom and the ones on the top here. But what if we attacked from the bottom? If we made our bromine here and it attacked from the top and it would the other bromine came in and attacked here, this one would open up, giving us our bromine on the bottom and our bromine on the top. Again, these are enantiomers of each other. Attacking one side gives you one enantiomer, attacking the other side gives you another enantiomer. That's with the cis. What happens if we do the trans? Okay, so now we have the trans, and so if we do the oxonium ion, the halonium ion on the top here, it's going to give us this one right here. And if we did the halonium ion on the bottom, it's going to give us this one here. Okay, but what's wrong with that? If we rotate this bromine up to this place right here, we now have a near plane. And so the trans-butene can give a meso compound. The cis-butene gives a racemic mixture of enantiomers. Okay, so that's the stereochemistry of the addition of chlorine or bromine across a double bond. So this is halogenation. Okay, so, but, once you form that, this cyclic system here, you can attack it with any nucleophile. We just happen to have bromine in the first one. And when we did that reaction, we did it with bromine or with chlorine in carbon tetrachloride, okay? A non-polar solvent that can't be halogenated. What if we did the reaction in water? It's a polar solvent and it can't be halogenated. And chlorine and bromine both dissolve in them. So if we did that, we could actually have attack by a different nucleophile once we form that bromonium, okay? And that would give us a halogen on one side and a nucleophile on the other. So that'd be something kind of little different there. So in that case, we would again get anti-addition because of the formation of this intermediate, okay? And the nucleophile will always attack on the more substituted carbon. Why? Well, because if they're the same right here, both of these carbons have the same electronegativity, right? Now, if they're different, if this one has carbons on it, you can, like this one had a couple carbons on it, there would actually be attack toward here because this bond that's going to break is polar, with this carbon being the more electropositive than this carbon because of donating effects. And therefore, it will attack the most substituted carbon right here. And you can do with any nucleophile. You can have sodium chloride in there. You could have alcohol in there. You could have base in there. Anything that can act as a nucleophile will. Your bromine's going to attack first, giving you this cyclic state, and then the nucleophile comes in second. So in this case, you want to have a lot of the second nucleophile. Okay, so we have a name for this reaction. It's called the Halohydrin reaction. It's where you add a halogen to it, and then you add water to it. And so what you end up with is a halogen on one carbon and an alcohol on the other. So what that looks like is you have bromine in water. Okay, so water is a poor nucleophile, but you're using it as a solvent, so there's a whole bunch of it. Okay, and so when you do that, it'll form the bromonium cation here in that three-membered state, and therefore you're going to have attack by the nucleophile from the bottom. So we're going to get that anti-addition, and in this case, we're going to get isomers, and we'll always get the trans isomers if you do a cyclic alkene. Okay. Let's see what happens when you have unsymmetrical alkenes, though. Okay. So what we're going to do is we're going to form that bromonium cation again, right here. And it turns out that this right here is going to be attacked by the water to give us our tertiary alcohol and our primary alkyl halide. So the bromine will end up on the less substituted carbon, and the nucleophile will end up on the more substituted carbon. Okay. So why? Okay. The whole reason comes down to that once we create this intermediate here, we have to think of these bonds as being kind of strained, right? We're trying to make a three-membered ring here. That's going to be a strain there. And so they're going to try to equilibrate that as much as they can. And so when they do that, it turns out that this carbon right here is going to be more electropositive than this carbon, because it's trying to pull that bond. It's an elongated bond. It looks like C. This bond is a little bit longer because it's more bonded to this one, giving this partially positive side, this a partially negative side. And it's more, this side has the partially positive charge because it's a tertiary carbon. This is a primary carbon, and therefore it's not going to have the more positive charge. And therefore your nucleophile attacks the more substituted carbon only. And then of course you have to lose a hydrogen to get to your product. Questions on that? So that's the halohydrin reaction. Same first step as the halogenation. You just changed what the nucleophile would be in the last step. Okay. But in the case of the halogen, you can't tell which carbon was which because they both have halogens on them. But if you do the halohydrin reaction and add water or alcohols, again, if you add alcohols, you're going to get an ether, just like in the hydration step. If you add alcohol, you'll get ethers. But in this case, you're going to get your nucleophile is always going to be on the more substituted carbon. Your halogen is going to be on the less substituted carbon. Okay. Okay. All right. So those are the reactions that are simply just adding across a double bond. Okay. So if we go back to the beginning of that table, we've done all of the ones on the right side. Now we're going to look at the ones on the left side of that table. Okay. So in the case of this, you can only get one alcohol by doing an addition across double bond using water, because the hydrogen goes on first, forms a carbocation, and then gives you this. So how do we get a diol? Well, we can get a diol by oxidizing that alkene and giving us oxygen on both sides. Okay. Now, I'm going to tell you right now, it's going to give us syn addition. And when you see the intermediate, you'll know why. Okay. So in this right here, we have a thing called osmium tetroxide and a little bit of base. And then you have something, a mild reducing agent on the end to break the intermediate. And that gives you cis diols. Okay. They're adding on the same side. So it's a cis diol. Okay. But why? Okay. The whole reason you get a cis diol is the first thing you do is you create this osmium ester. So it's an osmonate. Okay. And the way it does that is it kind of adds across the double bond. And instead of forming a three-membered ring like the bromine, it forms a five-membered ring because there's two oxygens on the osmium that can bind to that. So now all we have to do is break these two bonds, and we're going to have both of those oxygens cis. Both of those oxygens are going to be on that same side of the ring, and we have our product here. So we have two oxygens, we have two alcohols, they're going to be cis, and they're going to be 1,2. So it's 1,2 diols from an alkene. Okay. Now, turns out that you can use the osmium catalytically if you use this right here, which is N-methyl morpholine N oxide, which looks like that right here. What this does is this will oxidize the osmium dioxide, which is what splits off of here, back to osmium tetroxide. And so you only need to use a little bit. It'll just keep recreating the osmium tetroxide. The osmium tetroxide will keep making this five-membered transition state. And when it makes that five-membered transition state, That's nice and stable. So we have to hit it with something to reduce it off. And then it gives us our diol. Okay. So that means we have to have this in solution with our system. All right, questions on that? Okay. So that's the first time we've made a diol out of these, but we're using a very special reaction. So when you see the osmium tetroxide, you'll know that that is going to give you a cis 1,2 diol. Okay. All right, so let's look at this. Let's do the summary here. Reactions that give 50-50 mixture of syn and anti. Hydrohalogenation. Why? Carbocation intermediate. Acid catalyzed hydration gives you 50-50 mixture. Why? Carbocation intermediate. Oxymercurization, demercurization. Your mercury stays on until the other addition, and then you have to oxidize off the mercury. So it gives you Markovnikovs, but it gives you a syn and anti addition. And then if you used alcohols, we call that alkoxymercurization, demercurization to make an ether. This one makes an ether. This one makes an alcohol. Okay, so all of those give us a mixture. What reactions give us syn addition only? The ones that kind of add across the double bond at the same time. So that's hydroboration oxidation, because we're adding the boron and the hydrogen across the double bond at the same time. So that's giving us syn addition. Catalytic hydrogenation from last chapter sits down on the catalyst, gives us syn addition. And then we have the syn only dihydroxylation with the osmium tetroxide, because we're forming that 5-membered intermediate and then breaking off the osmium and generating our 2 alcohols. And then let's look at things that only give anti-addition. Halogenation and halohydrin formation. So if we break this down, this is because of carbocation. Okay. This is because it adds across the double bond all at the same time. So that it has a different transition state. And this one is anti because we form our intermediate that blocks one side or the other of the alkene. And so we always get anti-addition. It has to come in from the bottom. So what I like to do in these reactions to make sure I understand the stereochemistry is I like to include in my reaction table in that thing, special things, what the intermediate is. If you show yourself the intermediate of this, you're going to say, well, it has to come off the other side. It has to be anti. You're going to show yourself that you have a carbocation and you remember that it has one on the top and bottom. It can go on the top or the bottom. So you'll know it'll give you a mixture. Oxymercurization is a special case. It's going to add either one way or the other. And then when it oxidizes off, it'll give us that. And then these are all syn addition because of their mechanisms. They're all going to add across the double bond at the same time. Okay. So I like to divide them into what the intermediate looks like, because it really helps you understand the stereochemistry. Okay. Okay. Questions? Okay. All right. So now we're going to switch gears a little bit, and we're going to talk about something else you can do with alkenes. You can also use reagents to actually cut the double bond across. Well, gosh, it has 2 bonds. Wouldn't it cut something else across? No, the alkene, the double bond, is more reactive. It has electrons not in between the 2 atoms, but above and below that plane. So it's more reactive. So we can actually take advantage of that to focus our reaction on the double bond and actually break the double bond apart. Okay, the first of these reactions is what we call ozonolysis. Okay, and so we're literally coming in and we're going to chop the double bond apart. If you have, depending on how your alkene substituted, it can give you ketones or aldehydes. Okay, so let's look at that. So the mechanism is you have this material here. And this does what we call a 1,3 dipolar addition to create this intermediate, okay? This intermediate is not very stable, and what it's going to do is it's going to rearrange, okay, to give you 2 oxygens on one side and 1 oxygen on the other side. And then all you have to do is use a reducing agent to break some of those oxygen bonds. And in this case, we're going to use zinc metal. So the zinc metal is actually going to turn into zinc +2. So it's going to lose 2 electrons. Or we can use this dimethyl sulfide. And what it's going to do is the sulfur wants to be bonded to oxygen, and so it's going to take one of these oxygens away. When it does that, it's going to leave 1 oxygen on one side, 1 oxygen on the other side, giving us carbonyl compounds, aldehydes or ketones. Okay. So how do you know which is which? Well, you look at your bond. If you have 2 R groups on your alkene, that side's going to generate the ketone. If you have 1 hydrogen and 1 R group here, that's going to give you the aldehyde. So if you have a hydrogen on your alkene, it'll give you an aldehyde and that. Notice this is in reducing conditions, okay? We're going to have another reaction that's in oxidizing conditions, and so it's not going to do this. So this is selective to give us aldehydes and ketones. All right. If we do it in a different solution, let's do a different reagent here. This is permanganate with base and water. And so what we're going to do here is permanganate is kind of like that osmium tetroxide. It has 4 of the groups there, and it's going to come and it's going to oxidize our alkene. It can be a cis or trans alkene, but it will not give an aldehyde. Notice that there's a hydrogen here and a hydrogen here. If we use the ozonation with the zinc and stuff, it would give us 2 aldehydes, but we don't get that. We get acetate ions or carboxylic acids. So what's happening here? Oh, well, let's see. It's oxidizing it to get to the aldehyde, but the aldehyde is reactive in these conditions, so it's oxidized down to a carboxylic acid. Okay, so if you have a hydrogen on your alkene, you're going to end up with a carboxylic acid from the permanganate reaction. Okay, but let's look at what happens here. If we have it here, we have 2 R groups, so it can't form a carboxylic acid because it's not going to oxidize off on those. We get a ketone. So if you have 2 carbons on that carbon of the alkene, you get a ketone, just like in ozonolysis. But in this case here, we have 2 hydrogens. So it would break off forming aldehyde, but then it immediately react to form a carboxylic acid called carbonic acid, which decomposes into CO2 and water. Okay. So this is another thing we can do. That alkene gives you the exact spot where you can put your carbonyl compounds, your aldehyde, your ketone, or in the case of the permanganate solution, your carboxylic acid, exactly right there. But notice it makes the size of the molecule smaller. You've taken off at least 1 carbon, in this case here, and you've taken it, broken into 2 halves. So you can make smaller molecules with this cleavage reaction. Okay. And so this is a lot easier to see when you look at it. And so this makes it a lot easier to see when you use it in a ring. So in the case here, if we look at this, we have 2 carbons bonded to that part of the alkene. So that means that's going to give us a ketone. Okay. And now we have, on this one, we have 1 carbon and 1 hydrogen. And we have osmium tetroxide and dissolving and dimethyl sulfide. So that's going to give us an aldehyde right here. Okay. And on the other side of the molecule, outside the ring, we have 2 hydrogens here and 2 carbons bonded to this one. So this one's going to also give us a ketone. And then this is going to give us an aldehyde, the smallest aldehyde we have from aldehyde. So we're converting alkenes into 2 carbonyl compounds. Okay. 2 carbonyl compounds. if you use permanganate, you're going to oxidize your aldehydes down to carboxylic acids. Okay, questions on that? Okay. All right. So what about alkynes? Do they react the same way alkenes do? Actually, they do. You have some of the same reactions that we have here. What you're going to do is you're going to react the first alkene, you're going to react the first pi bond, and then you're going to react the second pi bond, and then you're going to end up with something, the products there. So let's look at halogenation first. Halogenation here, we're going to create our bromonium cation up here, and that's going to give us a trans addition. We're going to get our dibromoalkene with a trans configuration. And then if you add another equivalent, so if you just had one equivalent, so you have 1 mole of this and 1 mole of that, it's going to go once, and it'll give you the dibromo complex. You add a second equivalent right here to it, it's going to add across the double bond again, giving you a tetrabromo complex. And this works with chlorine as well. So you can do it. Now, remember, because we're doing that same mechanism, we're forming that cation right here, we're going to get a trans addition, giving us our trans alkene. So we're starting to see a lot of similarities in some of the reactions, right? So we're seeing them go through. And then when we look at our hydrohalogenation, we're going to see what we saw before in the halogenation reaction. We're going to have the halogen add to the more substituted side. Oh wait, it's acetylene. We can't add it to a more substituted side. If these are both C's, they're the same. If these are both H's, they're the same. But if there's an H on this side, we're going to add the H to the side with the H. It's going to follow Markovnikovs rule, and we'll have an alkane. But if we have it di-substituted, then we're not going to really know which one it's going to have. And we're going to get this addition here, and it'll be a trans addition. It follows Markovnikovs rule. And then, because we now have a hydrogen here, when we add our next equivalent, we're going to get both hydrogens on the same carbon. So it does follow Markovnikovs rule, and it gives us our geminal dihalide. Remember, there are 2 ways to make alkynes: geminal dihalides and vicinal dihalides. Okay, we made vicinal dihalides with the halogenation reaction of an alkene. To make the geminal dihalides, we actually have to do a hydrohalogenation twice on an alkyne. So that's important. That might be something to look at, add a reaction to your thing saying, hey, this gives me vicinal dihalides. This one gives me geminal dihalides. When you put it into your reaction table. Okay. So let's see what happens when we do our oxidation reaction. If we do our oxidation reaction with ozone here, it's going to break it apart and only give us carboxylic acids. Oh, wait, there's only 1 carbon hooked up here to each of these, so we can't get an aldehyde or a ketone because there's only 1 carbon on that acetylene. So that means we'll only get carboxylic acids out of it. Now, if it's symmetrical, you're going to get the same carboxylic acid, just 2 equivalents of it. If it's unsymmetrical, you're going to get 2 different carboxylic acids. And so then you'll have to figure out a way to separate. So let's look at this unsymmetrical one here. When we do that, we're going to break this double bond, giving us a carboxylic acid. So this is going to be the first carboxylic acid is this side. And this right here is going to break down to carbonic acid, which is CO3H2, and then that decomposes into CO2 and water. So ozone turns alkynes into carboxylic acids. So in the back of your book, you have this summary right here. How to make alkynes, how to use alkynes to make different tetrasubstituted or disubstituted, the Lindlar's catalyst, the dissolving metal catalyst, the regular reduction catalyst. We're actually not doing carbines, so you don't have to do those, but you get carboxylic acids over here, aldehydes and ketones over here. So knowing those different reactions and what their products are, and being able to say, oh, if I have an alkene and I do a reducing ozonolysis with this reagent, I can get aldehydes and ketones. Okay. So let's talk about retrosynthesis again. Okay. So when we're talking about retrosynthesis, I give you the product and I tell you something that you can start with, okay? So the first thing you want to do is look at the product and the starting materials you have. How many carbon differences do you see? Is the product bigger or smaller than the starting material? Okay, so in this case here, we're talking about synthesis, so we're going to try to add more carbons to our product than we have in our. So if the product has more carbon-carbon pi bonds than the starting material, then you're looking at, you must have one or more carbon-carbon bond form things. So think of acetylide ions or some other nucleophile. Then you want to match the carbons of the starting material to the product and see where those functional group changes are. Remember, I want you to look for the change in the thing. Not worrying about, oh, there's this hexyl group over here. It didn't change, so I shouldn't worry about it. I should only worry about the part that changed. So you want to analyze what changes. Concentrate on the functional group from the starting material and the products, okay? Because you want to see what starting material is in your product. You need to figure out what starting material you can use, what functional group can you use to make that final functional group. And then you work backwards from the product. You figure out what would be the step before that, and then you figure out what would be the step before that, and then the step before that. And you keep writing it that way until you've got it all the way back to things you're allowed to use, the skeletons of your starting materials you're allowed to use. And then you start it with, okay, now I know what my starting material is. These are my reagents. This is my intermediate. These are my reagents. This is my intermediate. These are my reagents. And this is my final product. Okay, that's where it comes in very handy to know your reactions forward and knowing just what reagent to add and knowing what the starting with the product and the reagent, knowing what the starting material was. That's why I want you to do it in both directions like that, because that way retrosynthesis becomes easier. Okay, so let's try to figure out how to do this one right here. Okay, so we have a starting material as hexanol, and our product is a dibromo cyclohexane, but we don't know what the stereochemistry is here. So we can make any dibromo compound we want. So that gives us a couple options. Okay, so first of all, how many carbons do we have in both? We have 6 carbons, so we don't have to make any new carbon-carbon bonds. Okay, great. So all we have to do is do a functional group conversion. Okay, so how can we make a 1,2 dibromo compound right here? Well, can't we take an alkene and add bromine to it? Doesn't that give us a 1,2 dibromo compound? So maybe bromine and an alkene are something we need here. Okay, so all right, so that means that one of our intermediates might be this right here. So now we have an alkene as an intermediate. How can we make alkenes from an alcohol? Oh wait, we can do the dehydration of an alcohol using, let's see, acid. H2SO4 is going to dehydrate this and give us our alkene. That'll give us the thing we can react to make our dibromo compound. Okay, so that means that we are going to, working backwards, know that we had to go back to this to make that. Then we knew we can make this from that. So that means our total synthesis goes, our alcohol is going to be dehydrated to give us our intermediate. We didn't know that was our intermediate until we backed up a step. And then we're going to brominate that to give us our final product. Okay. Questions on that? So when we're going to do some more practice problems, when we get, I want you to kind of digest this, and we're going to have a quiz next week. Yeah, next Wednesday. We'll have our quiz next Wednesday, and we'll be able to do some more examples of this on Monday. But this is all the slides for chapter 8. We're going to do some problems on Monday, and then there'll be a quiz with this on it on Wednesday. Okay, and that's pretty close. So any questions? Okay. So definitely go and do your reaction table over the weekend. Get it done, because I could give you a reaction table, but you building it yourself makes you remember it again and again and again, looking for the. Yeah, come up and get exams are on that table over there. Quizzes are on this table if you came in late. All right, thank you very much. No questions online? Okay, I'm going to stop sharing and stop recording.